Welcome to the Research Edge Forum for the month of April. Our first speaker this afternoon is Dr. Cheyanne Harvey. She currently serves as the Assistant Director in the Office of Recruitment and Admissions at the University of the Bahamas, Northern Bahamas campus. Dr. Harvey's research interest grew out of her desire to see ethical decision-making in the workplace and to determine what can be done to mitigate ethical lapses in the workplace. Dr. Harvey's quantitative research is entitled Differences in Attitudes Towards Ethical Decision-Making. Work experience in business ethics education among MBA graduates. The study explored the transfer effects of business ethics education in the workplace to provide businesses and academia tools to improve ethical decision-making in the work environment. Dr. Harvey believes that we should always be concerned with how our actions affect others within the organization and society. Stevenson, 2017. Please join me in welcoming Dr. Cheyanne Harvey. Dr. Harvey.
Good morning. Well, good afternoon, everyone. Thank you so much, Ms. Moxie, for having me, you and your team, including Ms. Natasha Williamson. So I will move right on to sharing my slide presentation for you. Okay, move on. Okay, so this is what the agenda for this presentation will look like. And of course, I'm not going to touch on each item on the agenda. All right, so looking at the introduction, we know that ethical lapses somehow appear to be ongoing in the business environment. In the business world, you have individuals and organizations, they are very concerned about unethical decision-making that they see. Scholars agree that it is still a major concern, and employees and managers, they are the ones that are faced with these dilemmas on a day-to-day basis, and sometimes it often leads to misconduct. According to the Ethics and Compliance Initiative, it appears that misconduct among employees seem to somehow worsen in looking at the historical findings. So there's an urgent need for companies to take the necessary precaution to improve misconduct. Now, looking at the background for the study, there seemed to be a moral and ethical decline in society from the 1960s, according to Sims. To kind of better understand what was happening, Ress and Kohlberg, they developed ethical decision-making and cognitive moral development models to try to understand why persons make unethical decisions. So by the time as the 1990s came around, there's been a whole wave of corporate scandals in the US in particular, and that's stemming from companies, particularly, I mean, among many others, of course, like Enron, Tycoon International, and WorldCom. So these companies were just plagued with scandals, greeds among corporation, fraudulent activities, and the list goes on and on when it comes to the unethical behavior. And of course, this has created a great distrust among the public. Continuing on with the background information, in the US in particular, they've reported losses of over 1 million, and we see that there's 1 in 3 corporations experiencing such losses. So scholars, as they continue on in their studies, they have concluded that, hey, this is still prevalent in the workplace. And it has only resulted in undesirable consequences, not just for the internal stakeholders, but also for persons and the environment. And other scholars agree, like Elaine and Pez, that this actually has contributed to the 2008 economic downturn that it was seen or experienced globally, So looking at the misconduct based on countries, we see that, many countries would have experienced this. Many employees would have experienced this within their organizations. And looking at the US in particular, it was at 30%. But by the time is 2020, it arose to 49%, where we had employees observe misconduct in the workplace. And these misconduct includes, but is not limited to, misusing confidential information, stealing, giving and accepting bribes, sexual harassment, conflict of interest, lying to employees, and even to external holders, and the list goes on. So we came across a situation where persons were pointing to higher education institutions to say, well, what is higher education institutions doing to kind of reduce the heightened lapses that we see? And institutions, of course, they began to embed it into ethics education, into their vision and mission and value statement, and even in co-curricular activities. Well, the Association for Advanced Collegiate Schools of Businesses, they began to increase that focus by incorporating it into their curriculum and coursework, from 2004. Nonetheless, scholars believe that higher education must produce graduates that perceive themselves as socially responsible. And only this would indicate whether the institution is meeting its moral purpose. So business ethics education really attempts to positively prepare graduates to handle these dilemmas that they will face in the workplace and how they can avoid it. So therefore, more research was needed, and looking at the gaps in prior research, I found that there were uncertainties about the transfer effect and whether business ethics education would persist over time in the workplace. Some other scholars believe that they want to look at the transfer effect and determine whether its responses are long lasting and how it impacts their careers. Others believe that it could have something to do, with age and business ethics education examining these variables. Other scholars like Tipton, 2016, he believed that, to better understand the relationship between business ethics, we have to look at MBA graduates and their future ethical reviews. Now, when trying to understand why I'm looking at business MBA graduates in particular, because the MBA program is one of the most sought after programs. We have there's over 700 MBA programs. In addition to that, a lot of the Fortune 500 companies, they plan on hiring a lot of MBA talents, because the salary alone starts at $115,000. And so this data was pulled from the Graduate Management Council in 2019. Now, looking at the problem statement, my problem statement was twofold. First, what was the prevailing issue in terms of whether attitude towards ethical decision-making differed between business ethics education among MBA graduates. The second prevailing issue from this problem statement was whether attitude towards ethical decision-making differed between length of work experience among this particular group. The purpose, of course, this was a quantitative, non-comparative, causal comparative, study. It's twofold again. The first was to determine whether the difference existed between the attitudes toward ethical decision-making and business ethics education among these MBA graduates. And then the second objective really was to determine whether there was a difference in attitudes towards ethical decision-making and length of work experience. So my research question focused on, to what extent, if any, was there a difference of attitudes towards ethical decision-making between business ethics education among groups, among MBA graduates in the US? And of course, I looked at who were employed full-time within an organization. So the null hypothesis was there was no statistical significant difference. And the alternative was there was a statistical significant difference among these groups. Research question 2, to what extent, if any, was there a difference of attitudes towards ethical decision-making between length of work experience groups among MBA graduates in the US who are employed full-time in business organization. Null hypothesis, there was no statistical significant difference. And then there was a statistical significant difference. So in looking at my variable, my independent variables was business ethics education. I measured it on a nominal scale. You'll notice that there were 4 categories. The first category was to determine whether persons receive formal business ethics education or training. And then the second one, would they receive informal business ethics education or training? Third, both formal or informal, and then neither formal nor formal. So this was the instrument that was used was a preliminary instrument. Looking at length of work experience is measured on an ordinal scale, and persons had different categories to fall into. For example, 0 to 5 years work experience, 6 to 10 years work experience, 3 to 15 or 15 or more. Again, that was used, the data instrument was the preliminary survey. Now, looking at my dependent variable, it is attitude towards ethical decision-making. Now, this was pulled from the defining issues test, in short, the DIT2 instrument. This instrument was developed by REST in 1998 and is just used to measure moral development. So looking at 3 stories, 3 recommended stories I use instead of the regular 5 stories. So the first dealt with famine, and it was, in short, where the father had to make a decision of whether or not to steal food to support his family. The reporter had to decide. She came up with, she discovered some information that can prove a bit detrimental to an aspiring politician. So she was wrestling with whether or not to release that information. And then the third was a cancer story of an elderly lady who was in dire pain, and the doctor had to decide. She wanted the shot. The doctor had to decide whether or not to give her the shot. Looking at my framework, again, I use REST, 4-step model for ethical decision making, and he believes that when it comes to ethical decision making, first there should be a moral issue identification, meaning identifying the moral issue, and then judging the moral issue, then conscientiously placing your moral concerns ahead of others, and then acting on those concerns. My research method, again, the method used was a quantitative study. The design was a non-experimental causal comparative study. The test was a Kruskal-Wallis H test, and the program was SPSS program to use to analyze my data. My target population was MBA graduates who are employed full-time in US business organizations. And again, I gave the rationale as to why I went with the MBA graduates in particular, because these are, the future leaders or even so the leaders in many business organizations. Convenience sample was used, so whoever met the criteria and who was available to complete the study, those were the persons that were used. Looking at the population, I targeted 244, but I ended up with only 177 after the scoring and the purging process. Overall, like I said, it was 177. My data was gathered from SurveyMonkey and Qualtrics. All right, in addition, data was analyzed, going through the cleaning process, the coding process, and then sending it on to the Center for Ethical Development for scoring. And then once I received that raw data, I was able to upload it into SPSS, and then I ran 2 statistical tests. One was descriptive frequencies, which would include all of the demographics, in addition to the independent variables, and then inferential statistics was used to run the Kruskal-Wallis test. And looking at my sample profile, most persons were in the range of 36 to 45. Most persons in this survey was males, and that's at 69.5%. Persons, their primary language was English, that stood at 98.8%. And this instrument also looked at political views of participants. So those who were neither liberal nor conservative, this was the highest percentage, which was at 25.4%. Looking at my descriptive statistics, both formal persons, most persons receive both formal and informal business ethics education training. You only had one person who received informal business ethics education training. Work experience, 6 to 11 years work experience. I had that was the highest frequency. So most persons fell into that range in terms of work experience. Now, these are the results from the independent variable, which is attitude towards, sorry, the dependent variable, which is attitude towards ethical decision making. So with that instrument, that will also, once the scores are received, once persons complete the survey and the scores are received, that will place them into one of the groups where it says personal interest, maintaining norms, or post-conventional. So for example, in this study, I found that there was 31.45. The mean was at 31.45, which was the highest. So they would fit into this personal interest, and it tells me that their moral decisions really is based on maintaining good relationships and for approval. And then for the maintaining norms at 29.42, it tells me that their decision making really is based on rules that are defined by society. And then post-conventional, 29.8%, would say that their moral decision is really based on based on the moral criteria. So this would, the 27.9 would be considered low moral reasoning. So if a person had moral reasoning of 41 or higher, that will be considered high moral reasoning. And these results are in keeping with the literature. Males tend to have, according to studies, low moral reasoning in comparison to females. My results, I found that there was no significance as it relates to the differences of attitude towards ethical decision-making between business ethics education groups. So there was no statistical significance that was found there. So in other words, business ethics training did not have any impact or influence on ethical decision-making among MBA graduates in the workplace. Research question 2, there was significant differences among these variables. Length of work experience actually appeared to influence attitude towards ethical decision-making in the workplace. So in taking my studies and then comparing it to other studies, overall, I found that the literature still appeared to be inconclusive regarding the impact of business ethics education. For example, some studies show that business ethics education or training does impact ethical decision-making in the workplace. And then some studies show that it does not impact ethical decision-making in the workplace. Some studies show that it has helped. One by Knowick 2018 shows that ethics education actually has helped recent graduates conquer the dilemmas that they face while employed. As you know, persons are, under pressure and so forth. So the training has helped them tremendously. And then when I look at research question 2, as it relates to the workplace and the ethical decision-making, there was no correlation for some studies. Some studies found that there were significant differences between the attitude towards ethical decision-making and increase in managerial work experience. So in other words, some studies show that the longer a person works, the more ethically focused and aware they will be. And so length experience appeared to contribute to attitude towards ethical decision-making. Some previous studies show that an increased awareness of ethics based on work experience. So ethics will create an increased awareness based on work experience. So looking at the theoretical implications, Ress, for example, he believes that age and education is very important in terms of determining ethical decision-making. So individuals, they approach moral issues differently based on some of where they are in terms of their cognitive development. Practical managerial implications. More and more, as we know, more and more companies, they are relying on data to make critical business decisions. So I believe that such findings should influence businesses and academia, to produce proceed with creating tailored programs that can assist with training in the workplace. I also believe that universities and they should incorporate more practical experiences for these business students in the curriculum. And we find that, the more years of work experience are accumulated, the greater the awareness of ethics will increase. And I know that you would have high school, persons, for example, coming straight out of high school and going into these programs. So that would be a great start, to try and incorporate more ethics training, because some of them may just going to school full time, but there should be some way where we can include certain work related or internship into the curriculum. And overall findings, it might even influence practitioners and firms, again, to collaboratively work together to encourage future growth and development, and that will produce better outcomes. And hopefully it'll be a start to reducing the ethical lapses that we see in the workplace. The strengths of the study, it's a quantitative research study. Non-comparative quantitative results tend to quantitative studies, tend to produce robust results. I also use the DIT instrument. This is a highly sophisticated instrument developed by REST, used in over 500 studies. In addition to that, it's been used on over 1 million studies, and it has added to the body of knowledge. But yet, like I say again, some studies show that, we're still only at the surface in terms of trying to understand business ethics education and its impact in the workplace. Looking at the study's limitation and weakness, I would say that, the sample size was not adequate, should have been a larger sample size. There may have even been possible bias from online surveys, because, sometimes participants tend to answer questions based on what they think the researcher may want to hear. And so they may be manipulating the test scores and so forth. And because this instrument was, I think there was about 90 questions, I'm not sure, and it calls for a concentration. I'm not sure what the conditions of which the participant took the survey were. So I had no way of verifying that. And again, I had no way of verifying that these were actual MBA graduates who took the survey, or just going based on, them meeting the criteria and what was submitted. My recommendation in conclusion would be to conduct a future research, and I would like to replicate the study in the Bahamian market, of course, as it was my initial desire, but things happen. I had to go back to doing it for the US. Using the extended version will not be a bad idea, because studies show that the extended version should produce better results. And future practice, again, recommendation is to just examine how work experience, now that we've discovered it, how work experience improves attitude towards ethical decision making. And overall, there's no one size that fits all when it comes to ethical decision making. So it'll be interesting, to see, what works best for per organization. Thank you very much again for your time.
Thank you very much, Dr. Harvey. It is indeed an area of research that I would say requires more study. I agree with you, especially in our market. Ethics is definitely an imperative, not only at the MBA level, but I also feel it's an imperative at the undergraduate level. And as a result, we have ensured in business that all of our programs are undergirded with business ethics courses, and that they get more than one of it, and that it undergirds most of our business courses. And so in addition to taking a course that focuses specifically on business ethics, because so often we find that ethical decision-making, people are taken aback that those at the highest level do not sometimes engage in ethical decision-making, and lies comes dressed up and highly educated. So, but thank you for your time. Thank you for your research. I'm always mindful that ethics is not what we do when people are watching. It is what we do when no one is watching. All the best to you as you continue your research in that area, and do look at your local market.
Yes, definitely.
Yes, 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 yes. So if you need to identify, maybe you need to remove the MBA and just look at master's degrees, and you would have a wider market, because if you look just at the MBA, I don't know that your pool would be as wide as you would want it. But
Right.
all the best to you as you continue your research, and thank you very much for being on the Research Edge Forum.
Thank
Do
you.
we have any questions? I see Dr. Watson's hand is up. Dr. Watson, you have the floor.
Thank you for that presentation. I thought it was very interesting.
Yeah.
I just had a question. One of the results you looked at how age and time of employment could lead to better results in terms of ethics. And I wonder if you controlled for something we see in the literature often. I know there's this, there may be some apparent conflict in the literature with respect to salaries and corruption. That's something that's well studied. And I think while there may be two sides of that, I think a lot of the literature shows that when people have higher salaries, and especially in jobs that are not well protected, unionized jobs where there's a high probability that they can be fired, they tend to be, corruption tends to lessen. So I wonder if perhaps you could explain your results through that lens, in that as a person goes through their career, their salary goes up, they have more to lose. They also have a shorter window in terms of if they are fired or make bad decisions. Starting over and finding a new job could be a bit more perilous as you get up there, up the ladder. So I'm wondering if that's something you have considered in terms of how do you control for that with your results?
Right. Well, looking at the salary, I haven't considered the salary. Again, the focus was mainly on those variables such as the business ethics education and how long they were in the work environment. And, it was still, like I said, inconclusive for some studies, because some believe, again, that there was a great impact as it relates to even the workplace. And then some, again, believe that there's no impact at all. But I would kind of agree that, sometimes the longer a person is in the workplace, the more likely they will become a bit corrupt in a sense, because, they have already comfortable in the work environment, and they may feel like, they can get away with certain things. So, I don't want to sound biased, but research has also shown that even with length of work experience, that should still be cautiously interpreted in some studies.
Oh, so your results, sorry, maybe I misinterpreted your results. I thought your results showed that the longer the person had been in the position, the corruption decreased, or ethics increased. They were more ethical, but you're saying they're less ethical.
No, the length of work experience, there was statistical significant with that particular study in terms of length of work experience and attitude towards business ethics education. So yes, the longer a person is in the workplace, I found that it creates a better awareness in my particular studies. But I was saying some studies show that the longer they're in the workplaces, actually it's more room for corruption, because they are comfortable in that work environment. They may feel that they can get away with certain things.
Right, certainly in those, I've seen similar things, but it tends to be in those environments where the risk of being fired or some major consequence, when those are low, then yes, corruption can still increase, or
right.
Misappropriation increases. When you know that if you step out of line, you may lose it all. People don't want to risk it all. Okay, I think it's very interesting.
Thank you.
Study that.
Are there any further questions? If there are no further questions, Dr. Harvey, thank you so much for your presentation. We are grateful for your presence at Research Edge.
Thank you for having me.
You're welcome. Our second speaker today is Professor Kevin Storr. He earned a Ph.D. in physics from Florida State University in Tallahassee, Florida. He is originally from the Bahamas and is currently a tenured associate professor of physics and coordinator of physics at Prairie View A&M University in Texas. His area of research involves low temperature, high magnetic field condensed matter, experimental physics with an emphasis on heavy fermion systems and graphene. Professor Storr has acquired and managed millions of dollars in research grant funding and has developed 2 research labs in 2 states in the United States. Professor Storr integrates his extensive and unique training as a professor and physicist in the development and presentation of his pedagogy for the advancement and assessment of science, leadership, and other areas of education. Let us welcome Dr. Storr to the Research Edge Forum. Dr. Storr, thank you for your presence and for joining us today.
Thank you, and good afternoon. Can everyone hear me?
Yes, we can hear you, Dr. Storr.
Okay, great. So I want to thank you all for inviting me to participate in your research forum, and I look forward to continuing to build on the relationship that's being developed here today. So today I'm going to be sharing briefly on thermal and magnetic studies of the heavy fermion superconductor, cerium cobalt indium 5, which is being doped with iron and neodymium. And so in the interest of time, I will kind of move through some of the slides and just hit the high points in order to be mindful of the time. So basic overview is that I'll give an introduction and background to material science, what are heavy fermions, also mention something about the low temperatures that we work with, the environment in which we functionalize our materials using temperature and magnetic fields and even doping. And then we will look at one particular type of measurement, which is heat capacity measurement as a means of detecting the superconducting state for this heavy fermion material, and also noting how, by applying a magnetic field, that we can move the critical temperature for the superconducting state towards lower temperatures, as well as suppress it with strong enough field. So what is material science? So in essence, material science basically involves studying the properties of matter. And so we look at the underlying structure of the material and its properties so that we can actually tune them for any functional purpose. This would involve things such as doping the material by adding other elements or compounds to it, which would adjust the properties that we see. This can involve applying magnetic fields, temperatures, etc. And so the whole idea is that by manipulating a material on an atomic level, on a microscopic level, that we are able to generate effects that would be valuable for different applications. And in some cases, applications are yet to be seen, but however, the fundamental science is put in place for any potential future work. So the ABCs of material science really begins with the periodic table, in that we take elements from the periodic table, which has different properties. And sorry, are you able to see my screen?
No, we can't.
Okay, well, I'll share it again. All right. Okay, are you able to see it now?
Yes, thanks.
Okay. So the ABCs of material science really involves the periodic table, whereby combining elements and subjecting them to pressures, fields, and other types of stimulus, we are able to induce radical properties in the materials. For example, simple example, that being, say, this water, that water in a liquid phase, we can convert water into a gaseous phase by simply adjusting the temperature, or we can convert it to ice by adjusting the temperature. Well, when we look at phases of matter, in terms of our materials, the types of phases we look at will tend to be electronic and magnetic phases, whereby a material may go from being a conductor to a semiconductor, or perhaps even a superconductor or an insulator. And these types of phases and changes can come about by simply applying different temperatures, fields, pressures, and even doping to our materials. So I'll just bypass that. So my interest really is the response of materials to doping, temperature, magnetic field, and pressure. And in terms of temperatures, we deal with cryogenic temperatures. And so I work with temperatures down to 20 millikelvin, which is very close to absolute zero. 20 millikelvin minus 459 degrees. In order to achieve these types of temperatures, we use really extravagant means. In this case would be something called a dilution refrigerator, which involves mixing two isotopes of helium, helium-3 and helium-4 in the correct proportions in order to get temperatures this low and even lower. In terms of magnetic fields, I work with magnetic fields up to 45 Tesla. For continuous fields, we've used higher fields at Los Alamos National Lab, which involves pulse magnetic fields, whereby these fields, they exist for fractions of a second. So to give you an idea, a 45 Tesla is basically 900,000 times the strength of the Earth's magnetic field, and roughly about 30 times stronger than a 1.5 Tesla MRI magnet. The materials that we've been looking at have been heavy fermion materials, and we're also moving into working with diamond films. So what are heavy fermion materials? Well, fermions are actually half integer spin particles. So half integer, meaning that their spins would be 1/2, 3/2, 5/2. And these obey what's called Fermi-Dirac statistics. And Fermi-Dirac statistics is applied to identical, indistinguishable particles which are in thermodynamical equilibrium, which also adhere to the Pauli exclusion principle, which is that we are unable to have more than one particle occupying the same quantum state. And so here we have the Fermi-Dirac equation, which again, from the interest of time, we'll minimize that. Now, so that's a fermion. So what is a heavy fermion? So in our materials, what is really king are the electrons. So as these electrons move through the materials, the electrons can have an effective mass, which is actually much larger than its rest mass. So to think of it this way, if you are being accelerated, that let's say maybe you're in a centrifuge of some sort and you're being spun rather rapidly, that a simple task of just lifting your hand would be more difficult for you, because at that point then you are experiencing this acceleration, which allows your weight to be more than you would experience just under the influence of gravity. Well, similarly, when you have an electron that's considered a heavy fermion, as it moves through the material and there's this background of other remaining items in there, that there will be forces that are acting on this electron, which would slow it down. In essence, it drags it along. So as a result, the electron moves as if it's much more massive than it actually is. So hence we refer to these as heavy fermion conduction electrons. And in the case of heavy fermion materials, electrons can experience these effective masses, which are up to 1,000 times larger than their rest mass. Now, one of the key things that we use is magnetic fields in order to induce states also as a means of allowing our material to undergo different phase changes. To get our magnetic fields, we basically use what's called a solenoid. And so a solenoid is basically simply a coil, and you run your current through the coil, and as a result of running a current through the coil, it will create a magnetic field along the long axis of the solenoid. If you run current down a straight wire, you will also be able to generate a magnetic field, which is generated around the wire itself. And then we have, of course, a permanent bar magnet. So in our system, we have a superconducting magnet, and the superconducting magnet is made up of material that has a very interesting property. And the property is that if you were to lower the temperature of the superconductor below what's called a critical temperature, what will happen is that the resistance of the material goes to zero. Now, with zero resistance, it means that the current can actually move through the wire without any type of resistance or without any impotence, and it provides full perfect conductivity. It also means that in a superconducting state, if I have the current persisting in the superconductor, I can actually disconnect the power supply, close the circuit, disconnect the power supply, and the current will continue to run indefinitely in that superconducting state. And the superconducting state persists as long as we are below the critical temperature for that superconductor. And so this is what a setup would look like, whereby this magnet would be housed in this dewar. This dewar would have liquid helium. Liquid helium is at 4.2 Kelvin. And at that low temperature, we are able to maintain the superconducting state of our magnet. The lab that I did the work in, this is the National High Magnetic Field Lab, which is located in Tallahassee, Florida, where I worked for some time. I did my graduate work there. Also, I have a lab that I've set up there that's still in existence. And so in this setup here, the platform here, this would be our magnet. And that dewar that I showed you actually hangs below this platform. And so this is the gas handling system for our dilution refrigerator, which allows us to get down to our low temperatures. And I told you about the helium-4, helium-3 mixture that's contained in this dump here that allows us to maintain our temperatures. Our samples are mounted onto a platform and it's attached to a rotator. This is a linear displacer. With the linear displacer, as it moves up and down, there's a spring that causes the platform to rotate so that we can study anisotropy for our materials. This is actually my lab, and so at the bottom here, this is our cryostat with our magnet. Our cryostat with our magnet along with the appreciable electronics. So the type of measurement that I want to emphasize for our heavy fermion materials is heat capacity measurement. So heat capacity is defined as the amount of heat needed to increase the temperature of a substance. So for example, if you were to have two different types of materials, maybe a piece of aluminum and a piece of iron, so both of them are, say, 1 kilogram, they're at room temperature. If you were to apply the same amount of heat for the same period of time, after, say, 2 minutes, and you were to check the temperature, you would find that the iron and the aluminum would have different temperatures. And the reason being is that the materials, they conduct heat at a different rate. So this is defined as the heat capacity, which is the amount of heat needed to increase the temperature of a substance. The specific heat capacity is simply the amount of heat needed to increase the temperature of a unit mass of substance by 1 degree Celsius or 1 Kelvin. So in order to actually measure any phase transitions in our heavy fermion materials, with the heat capacity measurements, what we do is that we begin to lower the temperature or increase the temperature of the material. As we lower the temperature, the heat capacity changes. Now, whenever a phase change occurs, when we say a phase change, simply means that, let's consider matter. Matter has solid, liquid, gas, or plasma. And if you were to deal with something simple, let's say ice, water, and steam, these have different heat capacities. So the amount of heat needed to actually change the temperature is different, but it's rather similar for ice and for steam, but for water, it's a bit higher. So as for ice, as you lower the temperature, as you take heat away from the system, the temperature is going to lower. Or as you add heat to ice, the temperature increases. So therefore, there's a correlation between heat loss and gain and temperature increase and decrease. Well, one would expect initially that as long as you continue to add heat to the ice, the temperature of the ice will increase. But in point of fact, that at the point whereby the ice is going to undergo a phase change from a solid into a liquid, that while the phase change is occurring, as you continue to add heat, what you will notice that the temperature will not change. And that's because at that point, the energy is being used from the chemistry side to basically break bonds or to bring bonds together, depending on which direction you're going with adding or changing heat. And that will continue to take place until the phase change has occurred. So the key thing is this: when you are undergoing a phase change as a result of adding heat to a system, the temperature of the system remains constant. So therefore, phase changes occur at constant temperatures. So at that point, then, what type of heat do we look for? We look for what is referred to as latent heat. And the word latent means hidden or unseen. It's hidden and unseen because you don't see it showing up in terms of a change in the temperature. So in terms of our material, this heavy fermion material, that this is being a superconductor, what we do is that we lower the temperature from room temperature. As we lower the temperature, the heat capacity is changing. But at the point where our material undergoes a phase change from the normal state to the superconducting state, then in that instance, then we should be able to measure the latent heat. And that latent heat shows up as a jump in the heat capacity. Well, superconductivity was actually discovered by a person by the name of Carmelin Onez. And interesting thing is that today is the 111th anniversary of the discovery of superconductivity, which was first seen on April 8, 1911. Just thought I would show that, put that in there. Now, I'm going to skip here to some of the data because of the time that we have involved. So here I have my heavy fermion material. This is cerium cobalt indium 5 that's been doped with iron. And so here we're taking heat capacity measurements. And with my heat capacity measurements, they're being done at different magnetic fields. So in the red legend here means that I had a magnetic field of 8.5 Tesla, 7.5 Tesla, 6.5, 4.5, 2.5, and all the way down to 0. And so as we begin to decrease the temperature, what we notice is that at a critical temperature that there's a jump in the heat capacity. And the reason why this jump occurs is because a phase change occurs. The phase change, in a different phase, the heat capacity in the superconducting state is different than the heat capacity in the normal state. So if I have any material, let's say any heavy fermion material, or even an organic conductor, etc., and I want to determine whether any phase changes occurred. Now, at this point, we may not even identify what the phase change is because we don't know exactly what to expect from a system. I would perform my heat capacity measurements, and what I'm looking for is a jump in the heat capacity. Once I see a jump in the heat capacity, which lets me know that I've now detected latent heats, and these latent heats are going to be really very high values. At that point, I know that now some phase change has occurred. At that point, I begin to study the material at that particular temperature and maybe applied field to determine the nature of that particular phase change. So what you'll notice is that as I begin to increase my magnetic field, so with a magnetic field, a constant magnetic field of 2.5 Tesla, that I have a jump in the heat capacity that occurs this is roughly at about maybe 2.2 Kelvin. This actually turned out to be the superconducting state. However, when I apply a magnetic field of 4.5 Tesla and I perform the same measurement, notice that the amplitude of my heat capacity for the phase change is actually lower, but in addition to which it occurs at a lower temperature. And if I were to go down to say 4.5 Tesla, that go down to the higher fields, that we see the same thing actually occurring at 8.5 Tesla. Here, notice that the superconducting temperature has actually gone towards lower temperatures. So this becomes a telltale sign for me that, one, I noted that I have a jump in my heat capacity, and this indicates my phase change. I am able to tune and move around my phase change for my material by actually applying a magnetic field. And then in addition to which, that this increased magnetic field, I am beginning to suppress the superconducting state. And as for a superconductor, I do know that superconductors, that a property of it would be magnetic flux exclusion, which is this. When you attempt to pass a magnetic field through a superconductor, the magnetic field passing through the area produces a magnetic flux. The superconductor wants to resist a change in that flux, so as a result, it will produce a diamagnetic field which will oppose that change in flux, so it will fight against it. However, there's only so much flux that the superconductor can produce. And if you keep increasing the magnetic field, eventually it will be able to penetrate the superconductor, and as a result, then we would be able to totally suppress superconductivity. In other words, I can destroy superconductivity by applying a magnetic field. So with this particular measurement of heat capacity, immediately I recognize I have a phase change. Two, I recognize that my phase change is dependent on magnetic field. As I increase the magnetic field, the critical temperature for the superconducting state occurs at lower temperature. But in addition to which, I begin to suppress the superconducting state. And eventually at a high enough magnetic field, I am able to totally suppress the superconductivity where it does not show up at all. Now, with this particular data, then I would be able to create what's called a phase diagram. With the phase diagram, I'm now taking the temperature at which the superconducting state occurred and the affiliated magnetic field. And by making a BT diagram, I have basically a phase diagram that lets me know that if I want to determine where I would be in terms of for the superconducting state, that it would be in this region right here. So we can intersect, so let's say at 1 Kelvin, that this would be a magnetic field at 10 Tesla. So therefore, my superconducting state for this material shows up at 1 Kelvin with a magnetic field of 10 Tesla. Whereas with a magnetic field of about maybe 6.25 Tesla, that the superconducting state would show up at about 1.6 Kelvin. So in the remaining minute, so we mentioned that the superconductor does not like to have magnetic fields penetrated. And so I show you this figure here at the bottom because this is a superconductor which is being cooled using liquid nitrogen. More than likely, it's probably YbCl, yttrium, barium, copper oxide. And this is a magnet. And the magnetic field of this magnet is attempting to penetrate the superconductor. But remember, the superconductor, it wants to resist the change in its magnetic flux. As a result, it will produce a diamagnetic field. And that diamagnetic field works against the field associated with this magnet, which causes it to levitate. This is a simple experiment we do with the students all the time. And you can pass like a piece of paper underneath it, whereby you can see that the material itself is actually levitating. And this was where we were going to show about how doping impacts superconductivity. But however, in our conclusion, we want to say that heat capacity measurements are used to detect different states of a system. So whether a system undergoes superconductivity, maybe an insulating state, or maybe acquires some magnetic state. They've been looking at the cerium-based compounds, which are known heavy fermion superconductors, which show unconventional superconductivity and quantum criticality. It is accepted that, that as key for these systems, that we're able to determine these exotic mixed superconducting states, and even with these FFLO, these fully ferro Larkin-of-Chinnikov, which unfortunately we didn't have time to talk about, and that the specific heat capacity of the material that we measured, along with showing that jump in the heat capacity, which represented the superconducting state, also shows a second anomalous jump in the heat capacity at lower temperatures, which is used to identify this exotic state called the fully ferro Larkin-of-Chinnikov state. So I thank you for your time, and I would take any questions that you may have.
Thank you very, very much, Dr. Storr. A very informative presentation. But you know, I'm from the business world, so I didn't understand all that technical stuff. So I'm going to leave that to Dr. Watson to tell me about it. But thank you so very much. Are there any questions for Dr. Storr? Dr. Storr, not one question. Dr. Watson, are you there?
I think he said that he had to go chair another meeting.
Oh, okay, okay, all right. Let me see who the scientists are in here. I believe I had seen Dr. Kabir.
Yes,
Dr.
I was. Yeah, I was about to tell Dr. Storr that I enjoyed, but I was on the road, so I kind of missed some part of your discussion. But I enjoyed that one. I have one question though. So when you are talking about the phase change, while you are changing the magnetic field and the temperature, so you're talking about the phase change related to the conductivity or the insulation state of that material. Am I right? Like how?
So that would be yes, yes, and no. I mean, so for example, if a material is if it's a conductor, then in that instance, as I lower the temperature, the conductivity will increase. If it's an insulator, the conductivity decreases. Now, in some cases, a material which is a conductor, by applying a magnetic field or by lowering the temperature, it would go from being a conductor into an insulator. So, so thereby you have your the resistance that you measure may be orders of magnitude higher after you cross over some temperature boundary or some field boundary. So in this case, we're looking at electronic and magnetic phases as distinct as you would see phases of matter as solid, liquid, and gas being distinct from each other.
Okay. All right. Okay.
Dr. Kabir?
Yes, I heard him. You hear me?
Yes. Do you have any questions?
Not anymore.
Okay.
Okay.
Dr. Storr, that's indicative of the fact that you did an excellent job. We thank you for your presence. We thank you for sharing your knowledge with us. We thank you for being at Research Edge Forum. Thank you all very much. Have a beautiful evening. Is there a question? Hold on, let me see. Oh, the question for you, Dr. Storr, is how can the findings from this study be applied in the real world?
Yeah, so it happens all the time. So for example, I will point you to your telephone, your cell phone. In your cell phone, there's some material called gallium arsenide. And when I was a graduate student, I studied gallium arsenide doing the same methods whereby applied a magnetic field to it, lowered the temperature. And so from those studies, there were countless other people studying the material as well. And by understanding those materials, now they show up here in your cell phone. When you purchase any piece of electronics and you get, say, the manual, normally the first thing we do is we throw the manual in the trash. But I think many people have seen this in the manual. It would say things such as this. This material is, this device will operate best under, it gives you a certain temperature range, right? So which means then that those materials have been studied, and they know that after you get to a certain high or low temperature, that the properties of the material will change. So I was watching a documentary one day when they were using a camcorder in this cave, and the temperature is very, very hot, very, very high. It was so high that the camera started malfunctioning, and that's because the temperature got so high, the materials in there, some of them became more conducting, some of them became more insulating. So when we study things such as this with these properties, then engineers, they know that they can use those materials in electronics or even in the medical profession. But however, people like me will say, this will work the way it's supposed to as long as you keep the temperature maybe between negative 40 degrees centigrade and positive 150 degrees centigrade. Above that, then now it starts acting in a different manner. So that's the value of the work that we do in studying these materials ahead of time so that they can be effectively used in everyday applications.
One more question, Dr. Storr. So what was the range of temperature you are working with? What millikelvins? Almost millikelvins, right?
Yes. So in my case, I have a dilution refrigerator that can go down to 20 millikelvin. Normally, the temperatures I work with, like 4 Kelvin is kind of high for me. I normally work in the range between about 1.5 Kelvin down to 20 millikelvin.
So you don't have any plan to use it in liquid nitrogen temperature? I think it's
well. So the thing with liquid nitrogen temperatures is that at that high of a temperature, then now you're dealing with a lot of thermal conductivity, which is going to, of course, to introduce more entropy. So as a result, you get higher resolution at lower temperatures. At lower temperatures, the more the positive ion gets frozen in, right? So in terms of conductivity, you have ionization. You have this positive ion. You have the electron. Positive ion has real large mass. So at those high of the temperatures, then you have this smearing background that overlaps and impacts what you measure from the electrons. And as you lower the temperature, the lattice gets frozen in, and you're really focusing on the electrons. So therefore, at liquid nitrogen temperatures, the value pops in that there are some superconductors now that will superconduct at temperatures above liquid nitrogen temperatures, which is actually good, right? But however, when you start getting on the quantum mechanical level, that you need the lower temperatures marching towards absolute zero.
Yeah, that's the difficulty, right?
Yeah.
Okay. Yeah. Thanks.
Dr. Storr, thank you very much. Very, very clear, very good presentation. Very enjoyable.
Thank you.
My question takes me a bit out of the superconductivity of the material that you're looking at. But you mentioned the heavy fermions and captivate my attention with that. Is the mechanism for the fermions changing their mass known?
Yes. So it's so when you consider heavy fermions, it's a rather well known and understood. They're basically you're looking at what's called the electronic correlations, and so with the electronic correlations, we're talking about the inner force of the electrons impacting the conductivity. So think of it this way: if you have the hallway at your building on campus, and if that long hallway is empty, then I can have a student just run down the hallway. They can move really very, very, very quickly. But now let's suppose I put some chairs randomly throughout the hallway and I tell them to run really fast. So in that case, then now as they attempt to move, they can't go in a straight line, so they're kind of taking this kind of zigzag effect. Well, now that's just them. But now let's suppose that they are like a big magnet running down the hallway, and there are other magnets in the hallway. And so as they run, as they get close to one magnet, they may get pulled towards it. Another magnet pushes them away. So it's going to impact the way how they actually move. So as a result, then the way how they move down the hallway with this background of other material that's there, they begin to move as if they are more massive than they actually are. So when we talk about heavy fermions, it simply means then that the electron is being impacted by other electrons, the environment, the impurities, so that it does not move as a free electron. So the free electron moving uninhibited, but rather it moves as if maybe someone has a cord attached to it and it's pulling on it to restrict its motion, so that it moves a bit more sluggishly, if you will.
What I am
as a result, then it moves as if it has a mass which is much larger than its resting mass, and that effective mass, that increase in the effective mass, is the basis of what we call heavy fermions.
So when I hear you describe it, I'm thinking resistance. Similar, like you have created resistance in the material, and we are now relating resistance to inertia. So are we saying that the electrical and magnetic properties of the material is somehow correlated to its inertia?
So the way how we look at it is that in terms of the model and the physics of it all, the electron, and just as you said, so the electron basically, it moves as if it has a mass that is much more massive than it actually is. So in essence, you would be correct in terms of how we relate it, say, to inertia. It's along the lines of when we talk about sound in metals and in materials, that we're not actually per se measuring sound, but instead, because sound is a compressional wave, and when we look at the lattice of the material, that it vibrates like in terms of springs, then in essence, the way how the energy moves through the system, it moves like that of sound. So therefore, we talk about sound in materials. So similarly, so they're looking at, you can call it the inertia or the resistance of the material, but then now we are measuring the mass of the electron. And when you measure these masses, you don't get the effective mass, but instead, the calculations work whereby the mass turns out to be much more than it actually is. So then the question is, then how do you account for it? So therefore, the working model of accounting for it is that the electrons are moving through a backdrop of interactions, which in essence is slowing it, pulling it, inertia resistance, so that it moves as if its mass is much more than it actually is. So the parallel that you gave with inertia and resistance, then yes, that would be a part of the model that we work with. It's a bit more involved than that, but that would be the basic starting point for understanding.
Are there any further questions for Dr. Storr? Dr. Storr, thank you so much for your presence here today. We are grateful for your presentation and for engaging in knowledge transfer. All the best to you. Thank you. Bye-bye.
All right. Thank you much.
Thank you all for being in this virtual space with us. We hope you've benefited from the presentations today. Bye-bye, everyone. Have a great weekend.